Okay, this is going to be the first of a few videos on the derivatives and the integrals of power series. And in this video, we'll look at, first of all, the derivatives. And a good first question, as always, this would be, why in the world would you want to find the derivative of a power series? And kind of the short answer is that in certain cases, it can make things a lot easier. Now, in this example, what we're going to do is this, we're going to find a power series for the cosine of x. Now, we did this already. We've done it in a previous video, but we did it the long way by using the full definition of a Taylor series. So we started with the cosine, and then to find each one of the coefficients, you had to find the first derivative, and the second derivative, and the third derivative, and the fourth derivative. Then you found the coefficient of the Taylor series, and eventually you came up with a power series for the cosine, but it took quite a bit of work. Now, what I hope you'll see in this video is watch how much easier it is if you do the following. Now, the idea is we're going to start with the power series for the sine, and if we take the derivative of the power series for the sine, it will quickly get you to the power series for the cosine. So let's run through this and you'll see the process is actually a pretty easy process. So first of all, begin with just the formal definition for the power series for the sine. So we'll go ahead and put that down. So you should know this, or you should at least be able to look it up in your book. The sine of x is a power series. In its expanded form, it looks like this. And over here on the right-hand side, you could also write it in summation notation. So it could be in either notation. And actually, as we do these, we're going to find it both in the expanded form and the summation form. So we'll do this. We'll put a couple of bars down the thing right here and divide it up into three parts. So in this center column, we'll do the expanded version of it. And in this column, we'll do the summation version of it. Now, it's all based on this, and this is something that you had way earlier in the course, and you should know this, that if you had the derivative with respect to x of the sine of x, and you already know that's equal to the cosine of x. That's something that you had way back when. So knowing this, what we're going to do is start with the sine. We'll take the derivative of the sine, but we're going to do it in the form of a power series, and that eventually should get us to the cosine. And we'll do it kind of a step at a time. So as we run across here, we'll do each step in each column. So first of all, I want to do this. I want to find, in this column, the derivative with respect to x of, I think I'll put it in brackets here, of the sine of x. So what that's going to be, it's going to be the derivative with respect to x, and you can just take this whole power series and put it in a bracket right here. So this would be minus, and I'll have x cubed divided by 3 factorial plus x to the 5th divided by 5 factorial minus, and so on. So you'll just take the derivative of each part. And then actually we'll do the same thing over here. We'll take the derivative with respect to x, if we were doing it in summation notation, and do the same thing over here. This is going to be the summation as the n equals 0 to infinity of, and you have minus 1 to the n, x to the 2n plus 1, divided by 2n plus 1 factorial. And then the whole thing will be in brackets. So the first step is just take the derivative of each one of these. Okay, what that's going to get you to, this would be the derivative with respect to x of the sine of x. Now, in this column, when you take derivatives of power series, you actually do what's called term-by-term differentiation. So just treat each term of this as if it was a power series or a power problem using the power rule for derivatives. So think of this as x to the first power. So the derivative of x is going to give you 1. Then you'll have minus, then on this one, the derivative of x cubed would be 3x squared. So again, just find the derivative of each term. And the 3 factorial is a constant. Then again, using the power rule, the derivative of x to the 5th would be 5x to the 4th divided by 5 factorial, and then minus, and so on. So that's called term-by-term differentiation. So the derivative of the first term, the derivative of the second term, the derivative of the third term, and so on. Now over here, we'll do the same thing. So suppose you were doing it in summation notation. Well, it's still going to be, in this case, when we find the derivative, it would be the summation And when we find the derivative, it's as if this part disappears. So from 0 to infinity. Again, treat the minus 1 to the n as if it was a constant. So it's going to be minus 1 to the n. Then all this is over. And we'll do the same thing that use the power rule here. So right now it's x to the 2n plus 1. So bring the old exponent down. So that exponent would be 2n plus 1. And now you'll have x raised to the, and if you started with this and take away 1, now it'll be to the 2n power. All divided by 2n plus 1 factorial. So you use the power rules on these terms, and you use the power rule here. You took the 2n plus 1, brought it down in front, and reduced the power by 1. Okay, now simplify it if you can. What that's going to give you, this part will stay the same. This is going to be 1, and then I'm going to think of each one of these factorials. You can express 3 as 3 times 2 factorial. You can express 5 as 5 times 4 factorial. So basically you're just factoring out one part of each one of those. Okay, so now let's go ahead and simplify this. So I've got, here's the, I'll put the equal to right here. Here's the 1. Now in this case, when I write it like this, I've changed it from 3 factorial to this form, so I'll draw a line through those. So in this case, the 3's will cancel out, and that's going to leave you with minus x squared divided by 2 factorial. Then here the 5's will cancel out, and it's going to leave you with plus x to the 4th divided by 4 factorial. And then minus and so on. And what you'll recognize, I hope, is that that's the power series for the cosine that you did earlier when you did the full Taylor series. And so this is going to be the cosine of x. So the derivative of the sine is the cosine. The derivative of this power series is this power series. And then finally, on this slide, it would look like this. It would be the summation as n goes from 0 to infinity. And now you'll still have the negative 1 to the n power. But in here, I'll rewrite this one. Here's a 2n plus 1, and I'm going to write this factorial as 2n plus 1 times 2n factorial. Doing the same thing right here. I just broke out a 5. Here I broke out a 3. Here break out the first term, which is 2n plus 1, then it becomes this. So you can write this in this form right here, and we'll draw a line through that. Okay, so what happens now, there's a 2n plus 1 on the top and a 2n plus 1 on the bottom. This one will cancel out this one, and in the bottom it'll leave you with 2n factorial. And then in the top you still got an x to the 2n factorial. And if you check in the book, in the tables in the book, if you check for the cosine, you'll see the cosine is, here's what it looks like in expanded form, here's what it looks like in summation form, and notice it was much easier to get. So this is one use of the derivatives of power series. If you know an original series like the sine of x, and you know that the derivative of the sine of x will get you to the cosine of x, then if you find the derivative of the power series, you can get the power series for the cosine without having to go through the whole full Taylor polynomial thing. So anyway, it just makes it a little bit easier. So that's the first example of how to find derivatives. And just also remember, as you take the derivative of a power series, it's what's called term-by-term differentiation. So take the derivative of the first term, the derivative of x is 1. The derivative of x cubed would be 3x squared and so on. So just do it term by term, and it makes it easy to get a solution here. And then what you're doing for the power series, you can do the same thing in summation notation. You're just doing it in general form. So again, there's a first example of how to use derivatives in power series, and we'll take a look at one more example of derivatives in the next video.